So let's go ahead and dive into Chapter 5, Section 3, Additional Properties of Binomial Distribution. Okay. All right, so your exam, you can have 2 dates for the option again. You can either take it Monday the 15th when you come back, and we'll announce this next week as well, or you can take it on the following Saturday, whatever works best for your individual schedules. But we will complete all of Chapter 6 next week, so be prepared to stay after class a little bit if we need to. Maybe some of the sections will be a little smaller and I can talk really fast. All right. Our focus points for this section will be making histograms for binomial distributions, computing mean and standard deviation for binomial distributions, and computing the minimum number of trials needed to achieve a given probability of success. Okay. Graphing a binomial distribution. Go ahead and read that. Let me know if you have any questions. Okay, so remember the binomial distribution tells us the probability of R successes out of n trials. Therefore, if you place values of R along the horizontal axis and values of P of R along the vertical, you will have something that looks kind of like, well, there's your procedure, which if you are someone that writes down the notes, you probably want to write that down. Okay. You want to remember to construct a bar over each R value extending from R minus 0.5 to R plus 0.5, and the height of this corresponding bar is P of R. So you guys can see that everything's kind of building on itself. So here's an example we're going to look at. A waiter at the Green Spot restaurant has learned from long experience that the probability of a lone diner will leave a tip is only 70%. During one lunch hour, the waiter serves 6 people who are dining by themselves. Make a graph of the binomial distribution that shows the probabilities that 0, 1, 2, 3, 4, 5, or all 6 of the lone diners leave a tip. Okay, so side note, first of all, you should always leave a tip unless certain situations arise. Number 1, if you have any kind of terrible service, you should not be leaving a tip. That's just basically reinforcing negative behavior. I almost got punched. Punched is slightly an exaggeration, but we were unsatisfied with our food and we went to talk to the manager and the waitress basically shoved her hand with our receipt into my chest. Like literally made contact with my chest. And like I literally scratched out the tip 3 times and finally walked away without leaving one because I really just couldn't bring myself to leave someone a tip who would physically put their hands on me. That being said, I also have to have like super ridiculously good service to leave a tip at a buffet because I feel like literally all they do is maybe bring me 2 drinks and then most of the time ignore me. So it's just kind of each their own, I guess. But I never not leave a tip if I'm eating by myself. It's not like my brain has never gone there. So I would definitely be in the 30% that I would always leave a tip, even if I was by myself. Okay, so here's what we have. We have n equal to 6, which is our trials, p equal to 0.7, which is our successes, meaning that they will leave a tip, and then q being the failures where they will not leave a tip. So they have gone through and they've figured out all of their probabilities, which at this point you should all be able to do. And then once they use the table, they're going to construct their histogram. So, I would think out of all of the sections in chapter 5, this one was probably going to be the easiest for you because it's literally taking what you just did in 5.2 and you're redoing it, but now you just figure out the graph. I could be wrong on that, but that's basically what it seems like on this end. Okay. So the probability of a particular value of R is given not only by the height of the bar over the R value, but also the area of the bar. Each bar is only 1 unit wide, so the area equals the height times the width. And then that means its area is also equal to the height. Since the area of each bar represents the probability of R under it, the sum of the areas must be equal to 1. 0.001. And the reason why it's not 1 is because of rounding error. You guys, this should be a repeat. We basically said this in the last section. Mean and standard deviation of a binomial distribution. 2 other features that help describe the graph of any distribution are the balance point of the distribution and the spread of the distribution about the balance point. So the balance point is just another description for the mean. And the measure of spread is another phrase for standard deviation. Don't forget that the mean can also be recognized as the expected value of the successes. Okay. All of this should be repeat for you. For the binomial distribution, we can use 2 special formulas to compute the mean and their standard deviation. Okay, you guys can write this down. So you can see that the mean here is a little bit different. You're just going to take n times p, and that the standard deviation again is a little different. You'll take the square root of n times p times q. So this one is a lot easier to to calculate than the other ways you've done it in the past. Okay. Oops. Okay. So let's just take an example here. If we're given n equals 6, our p is 0.7 and our q is 0.3. If we wanted to find the mean, we're just going to take n times p, which is 6 times 0.7, and you get 4.2. Before we show it, let's go ahead and figure out what our sigma would be. We would take the square root . We would take the square root of n times p times q, which would be, you can either notice that you'll have 4.2 again, or you could write them all out. 6 times 0.7 times 0.3. So we get the square root of, so 6 times 0.7 times 0.3 will give us 1.26. And if we take the square root of that, we get roughly 1.12. They may have chosen to just say 1.1. We will have to take a look at where they chose to stop. Typically, conventionally, when you're dealing with decimals and you're dealing with it at this level, the best thing for you to do would be to go 1 more than what they give you. So they gave us 1 already, like they gave us to the tens. So for me, I would feel much more comfortable if you had the hundredths, but they may choose to also go to the tens. Oh, look, see, great. They followed our rule. Any questions on that? No? Okay. If I have time today, I'll go ahead and start chapter 6 as well, but I don't know how long 5.4 is. So quota problems, minimum number of trials for a given probability. In applications, you do not want to confuse the expected value of R with certain probabilities associated with R. Quotas occur in many aspects of life. The one that we all probably can think of and hate the most is at the end of the month, cops always have to meet their quota. So, especially young drivers, and I'm speaking massively from experience, young drivers can get pulled over quite a lot at the end of the month. Obviously, along with speeders and anyone who drives a colored car that is not, the norm. In some districts, people have a monthly quota for the number of traffic tickets issued. Nonprofit organizations have recruitment quotas for donations or new volunteers. This basic idea uses complete quotas and can also be used in medical sciences. So how frequently do checkups occur, quality control, risk management. To have adequate power, a satellite must have a quota of 3 working solar cells. That's something interesting. Such problems come from many different sources, but they all have one thing in common. They are solved using binomial probability distribution, which makes sense because you're either going to have a success or a failure, right? To solve quota problems, it is often helpful to use equivalent formulas for expressing binomial probabilities. These formulas involve the complement rule and the fact that binomial events are independent. So let's look at the example. If you guys write your notes, you will want to write this procedure down. It will definitely help you with your homework. And this is probably where your brains are going to start going, this is the statistics that I assumed we were eventually going to get to. So if you want the probability of at least one success, you take the fact that at least one means that you're going to have one or more. So what you're not going to have is the probability of 0. So if you take 1 minus the probability of 0, that will give you the probability of 1 or more. Same thing with probability of at least 2, 3, and so on. Okay. So basically a domino effect. Once you understand how to do it one way, you just have to keep subtracting until you figure out each of your answers. Okay. All right, let's look at example 9. Junk bonds can be profitable as well as risky. Why are investors willing to consider junk bonds? Suppose you can buy junk bonds at a tremendous discount. You try to choose good companies with a good product. The company should have done well, but for some reason did not. Suppose you consider companies with a 35% estimated risk of default, and your financial investment goal requires 4 bonds to be good bonds in the sense that they will not default before a certain date. Remember, junk bonds that do not default are usually very profitable because they can carry a very high rate of return. The other bonds in your assessment group can default or not without harming your investment plan. So as long as you have 4 bonds, you should be good. Suppose you want a 95% certain of meeting your goal quota of at least 4 good bonds. How many junk bonds issues should you buy to meet this goal? So go ahead and take a look at that. Okay, since the probability of default is 35%, the probability of good bond is 65%. Let's success be S, and that would represent a good bond. You can literally represent your stuff any way you felt comfortable. A lot of times they use S because of success and F for failure. But if you really wanted to do good bond, so GB versus, I don't know, a bad bond for BB, you could do it however you wanted. Let N be the number of bonds purchased and R be the number of good bonds in this group. We want the probability of R greater than or equal to 4, greater than or equal to 95. This is equivalent to the following. Since the probability of successes is P equal to P of S equals 0.65, and we need to look at the binomial table under P equals 0.65 and different values of N to find the smallest value of N that will satisfy the preceding relation. Okay, so if you have access to a printer, any of these tables that they mentioned is going to be a lot nicer to you if you can kind of draw on them, or at least, use your fingers and do a drop down and over. If you have a tablet and you can write on your tablet, you could open it on your tablet. If you can handle it on the computer, that's good for you. My eyesight's getting a little bit too bad that I can't do that. So basically you go to table 3 of appendix 2 shows that N equals 10 when P equals 0.65. Then you get the following. The probability that 0.975 satisfies the condition of being greater than or equal to 0.95. We see that 10 is the smallest value of N for which the condition is satisfied. So if you had a larger sample size, you would maybe get a better probability, but it's going to take a lot to even move a little. So 10 is probably your best option there. Right. And the program should almost always give you an idea of if you have to use a table or not. It'll either give it to you in a way that you can use it as a pop-up, or it will express to you where you can find it in the textbook. All right. Do we need this? I don't think we need this. And it's done. Okay. So basically all this is saying is that if you buy 10 carefully selected junk bonds, then you have a probability of getting at least 4 of them to be good ones. All right. Let's go to 5.4. All right, the geometric and Poisson probability distributions. These, for the most part, should kind of be plug and chug. I don't really think you'll have to do anything outside of that, but we will give it a whirl. In many activities, the first to succeed wins everything. Using the geometric distribution to compute the probability that the nth trial is the first success. Use the Poisson distribution to compute the probability of the occurrences of events spread out over time or space, and use the Poisson distribution to approximate the binomial distribution when the number of trials is large and the probability of success is small. Okay. I can't remember, but I feel like sometimes this section is optional. So if we don't have anything on the test from it, I will let you know, but for right now, I would just work with it. It might just end up being an easy homework for you. Suppose we have an experiment in which we repeat binomial trials until we get our first success, and then we stop. Let N be the number of the trial on which we get our first success. In this context, N is not a fixed number. In fact, N could be any of the numbers. What is the probability that our first success comes on the nth trial? The answer is given by the geometric probability distribution. So here is your definition. Here you can see you have a different way of finding mean and a different way of finding standard deviation. You have 1 over p, and then you also have the square root of 1 minus p, which you would know as q, divided by p. Okay. You're also given the distribution itself as P of n equal to P times the quantity 1 minus P raised to the n minus 1. Again, for some reason, they only use P's here. They do not bring in your Q. Okay, let me know when you are all good on that front. Okay. Going to assume those of you that write it down are good to go. Let's take a look at this example. I'm sure we'll work through one. An automobile assembly plant produces sheet metal door panels. Each panel moves on an assembly line. As the panel passes a robot, a mechanical arm will perform spot welding at different locations. Each location has a magnetic dot painted where the weld is to be made. The robot is programmed to locate the magnetic dot and perform the weld. However, experience shows that on each trial, the robot is only 85% successful at locating the dot. If it cannot locate the magnetic dot, it is programmed to try again. The robot will keep trying until it finds the dot and does the weld, or the door panel passes out of the robot's reach. What is the probability that the robot's first success will be on attempts 1, 2, or 3? Since the robot will keep trying until it is successful, the geometric distribution is appropriate. So because we don't know if it'll be a success on the first try, the second, or the third, then your brain should think geometric. We literally just plug everything in. You will see your 3 probabilities spit out. Next question says the assembly line moves so fast that the robot has a maximum of only 3 chances before the door panel is out of reach. What is the probability that the robot will be successful before the door panel is out of reach? So basically, you would have to just add up your all 3 probabilities. So it looks like the robot overall is doing a significantly good job. So, questions on how they found that out? No? Okay. So this would just be taking it one step further and looking at how you would interpret this. The probability of the robot will correctly locate the weld. We just found that from part B. So the probability that it does not and is unsuccessful is 1 minus the probability we just found. So you're only looking at 0.34%. Right? And then you would multiply that by the 10,000 and you only get 34 defected doors. It could have a range there, and that would of course be due to error. All right, Poisson probability distribution, a little bit different, named after one of our French mathematicians. I'm not going to try to pronounce the French pronunciation of that. Outside of probabilities, he also did a significant amount of work in physics, and a lot of his math, relates back to that. Okay. So just like we have a success and a failure, A particular event occurs is a success and does not occur as a failure. The events that need to be independent so that one success does not change the probability of another success during the specified interval. Okay, so Poisson is always going to be something you'll be able to recognize because it uses, I believe that's lambda. Yes. So if you see lambda in the work or in what you're given, then you should be doing Poisson distribution. So here's how you find your probability. You take e raised to the negative lambda times lambda raised to the r all over r factorial. Mean is going to be equal to your lambda, and sigma is going to be equal to the square root of your lambda. Again, if you write your notes, make sure that you are writing this stuff out. If you're someone that uses the note cards or the sheet of paper for the exam, you probably want to write it out on there as well. Okay. All right. Let's look at this example. I believe this will be the last example. I don't think it goes too much further in depth on these. Pyramid Lake is located in Nevada. The lake is described as a lovely jewel in a beautiful desert setting. In addition to being a natural beauty, the lake contains some of the world's largest cutthroat trout. 8 to 10 pound trout are not uncommon, and 12 to 15 pound trophies are taken each season. The Indian nation there uses highly trained fish biologists to study and maintain this famous fishery. In one of its publications, the following information is given about the November catch for boat fishermen. So the total fish per hour was 0.667. Suppose you decide to fish Pyramid Lake for 7 hours during the month of November. Use the information provided in the fishery biologist to find a probability. To find a probability distribution for R, the number of fish of all sizes you can catch in a period of 7 hours. So the success rate is 0.667 over 1, which means 0.667 will be our lambda. Since we want to study a 7-hour interval, we will use the arithmetic to adjust lambda to 7 hours. So 4.7 for a 7-hour period. All right. And that just kind of breaks it down for you. Right. Then you're going to just go ahead and plug in. Again, they give you this approximation. You could just use the E on your calculator. It will work just as fine. Then you have to plug in the different options here for R. So you will end up with multiple probabilities. So the first one for part A, you'll get probability of 0 is going to be 0.01. So 1%. If you were out on the lake for 7 hours and you catch absolutely nothing, you probably weren't actually fishing. You probably put the pole in one time and then you sat there and read, or you sunbathed, or you did something else, because obviously the lake is so numerous that you would not walk away without a fish. Although I would probably walk away without a fish. Okay, so now you're looking at for 1 hour or one fish at least. In the 7 hours, you're looking at about 4%. And for 2 hours, you're looking at 10%. And for 3 hours, you're looking at 16%. All right. Or sorry, 3 fish. It's all within 7 hours. So more than likely, if you're fishing for 7 hours, you're going to get a large amount of fish in that amount of time. Okay. All right. What is the probability that you will get 4 or more fish? So remember here, we're going to just use our complements. So if it's 4 or more, that means you're going to do 1 minus everything under 4. So 69% chance that you will catch 4 or more fish in a 7-hour period. That makes more sense. Okay. Do we need this? Basically, if you're dealing with large number sizes, Poisson is going to be your best bet. You're going to take n times p to find lambda, as long as n is larger than 100, larger than or equal to 100, and n times p is less than 10. Okay, here's your procedure. You definitely want to write it down. I am more than certain that it'll end up on your homework. Okay, so n is your number of trials, r is your number of successes, p is the probability of success for each trial, n has to be greater than or equal to 100, n times p has to be greater than 10, then r has the binomial distribution, and we can use lambda equal to n times p. There's your probability. And note that lambda equal to n times p is the expected value of the distribution. It's not the lambda you're actually going to use. Okay? Questions? All right. Okay. Let's take a quick look at this. 16 personality types are discussed in the book, which if any of you have taken psych or are thinking of taking psych, you will discuss Myers-Briggs. One of the more rare types is introverted, intuitive, feeling, and judgmental, which is only about 2.1% of the population. Suppose a high school graduating class has 167 students, and suppose we call success the event that a student has this rare personality type. So you will take n equal to 167, which is your graduating class. The probability of success is equal to 0.021, and we have to determine if Poisson is the best approach. So n, of course, is greater than 100. N times p gives us 3.5, which is less than 10. So then the Poisson distribution is good. You can go ahead and plug all this in. You know now how to get all of these probabilities. And then if you really needed to know the other version, then you would just subtract. Okay? Here's it the opposite way. All right. That is the end of chapter 5. If you guys need longer with that, you can always watch the video later whenever you are studying. Does anyone have any questions for me on that? No? Good. Okay, I'm going to pause the recording.